Welcome back. Today we're going to look at how to solve multi-force problems, and we're going to start out by talking about the force of gravity as one specific force that is in every single problem you will solve. And so I'm going to start over here with a summary of one of the lectures I gave, which was on the gravitational field strength. And what I want you to consider is if we take this as the Earth, and we have 4 people distributed around the Earth, North Pole, South Pole, then East and West, they all view down in a different orientation if you view it from way out here. But relative to the surface, the gravitational field, which I have in light purple here, always pulls toward the center of the planet. So what's going to happen is when you look at this on a scale where we operate, we function, the Earth essentially looks pretty flat to us. So we don't see the curve. So these lines that are called, they're radial, they point in toward the center of the planet along radius lines. Essentially, those are going to look like straight down. So a downward vertical orientation. Now this field strength acts on any mass within the field because it's a field strength that depends upon the mass of both the Earth and the object. So the reason you are left on the surface is because there's something pulling you down, and if there was no ground beneath you, you would keep moving toward the center of the planet. The force produced by the ground is an aspect we will look at in a subsequent lecture. But even for the skydiver, they fall. If they're falling, there has to be a force on them making them fall, so they don't have to be in contact with the Earth. Raindrops, same thing. They fall downwards because that's the way the gravitational field is pulling them. Gravitational fields on a planet are always going to pull objects down toward the center of the planet if they're not already on the surface. So it's good to start with this because in every single problem we look at, you're always going to have a force of gravitation on something. So when we look at the gravitational force, I talked about kind of viewing this as a force field, tractor beam. It's going to act without directly touching the object. It's going to pull on mass. Gravitational fields pull on mass. The equation we use is going to look like this. The gravitational force, capital F, little g, can be calculated if you know the mass of the object in kilograms, and then the strength of the field of whatever planet you're on multiplied by that mass. And it turns out that the gravitational field strength, we're going to use an approximation here. If you're near the surface of the Earth, 1 kilogram of mass, if you put that on a bathroom scale and it could measure the weight in newtons, it would read 10 newtons. So every 1 kilogram of mass is going to feel a downward force of 10 newtons. So negative 10 just means 10 down. So 2 kilograms of mass is going to feel 20 newtons down pulling it. 3 kilograms of mass, negative 30, or 30 down. So keep that in mind. The weight equation is what we're going to focus on right now. So you can calculate the weight of any object at or near the surface of the Earth if you know the mass of the object, because we know the weight equation. And that g value doesn't change. On the Earth, it's negative 10. Technically, it's negative 9.81. We round up to negative 10. And there is a reason it is also equivalent to the acceleration free fall, but I'm not going to go into that quite yet. I think this is a better way to learn it. So the field strength is here. So every 1 kilogram of mass is going to feel 10 newtons of force pulling it down. And so what I want to look at is you can calculate the weight of any object, mass times negative 10 basically. That's the short way to talk about it. But we want to look at drawing the way these forces act. So free body diagrams of force arrows. So for the case here, we have an object, and I only want to look at just the gravitational force. That's it. So I'm going to ignore what's happening with the ground. If this person has a mass of 70 kg and I want to know what's the weight, I can either say what's the force of gravitation acting on the person, or what is the weight. 70 kg times negative 10 per 1 kg. And this is a kg over here. So you're going to have 700 newtons. Let's try that again. It's going to feel a 700 Newton force pulling down. And that's what this person would feel, pulling them or holding them against the ground. If we took a skydiver and said that their mass is 120 kilograms because they're wearing more gear, this is going to do the same thing. The mass is 120 kg. I'll do it out with the units now so you can see a little more fully. And it's going to be 10 newtons down per every 1 kg. So this person's going to feel a force of 1,200 newtons down as they fall. The only reason that the number's larger here, remember negative is just down, is because this is more massive. This person is in free fall. I'm assuming no air resistance here, even though I show like the drag lines here. This is still being acted upon, which is why something in the air above the earth will fall down. If you're already on the surface of the earth, you can't fall down anymore. So there is a case where you can have forces pulling on something, but it may not move. And you're going to see that if you read the write-up on A23. There's a couple of introductory pages of this information. So the big thing here is a summary of gravitational force is present everywhere. You can call it weight. It means the same thing. It's the weight, the force that the Earth puts on another mass. It's always going to be 10 newtons down per kilogram of mass. And this is the weight equation. That's where I want to start, because this equation is where everything's going to start happening.